Hello, welcome to today's video. There is a handout. If you want to print the handout, just try not to peek at it until I tell you, because the lesson's more interesting if you haven't seen the work ahead of time. All right, so let's get started. Section 5.5 has more formulas, more identities, double angle formulas. So here are the first two. Here is a double angle formula for sine and a double angle formula for cosine. The textbook uses u, so I used u. You could use theta, you could use x, you could use any variable you want here. And that's not sine squared. That's sine of 2u. The 2u is inside of the sine function. So the sine of 2u is equal to 2 times the sine of u times the cosine of u. And a formula for cosine 2u is cosine squared u minus sine squared u. And what's kind of neat about these formulas, in my opinion, is that you can pretty easily derive them. That's not derive. The word is derive. So based on things you already know, you can actually figure out these formulas. So here's where the sine 2u formula comes from. 2u is equivalent to u plus u, because u plus u is 2u. So if you rewrite 2u as u plus u, you can use the formula from section 5.4 to expand and make it sine u cos u plus sine u cos u, and that gives you 2 sine u cosine u. So even if we were in school, this is a formula that I would say don't memorize. You certainly don't have to memorize it because of the way we're doing our learning. But even if we were in school, I'd say don't memorize this formula, just derive it because it's so quick. Similarly, with the cosine double angle formula, cosine 2u, since 2u can be rewritten as u plus u, you can just apply your cosine angle sum formula. It's cos minus sine, and that's how we got that. Now, there's a couple other versions of the cosine double angle formula. There's 2 cosine squared u and 1 minus sine squared u. And I bet you can figure out where those come from. You can actually derive those from cosine squared u minus sine squared u. When you see squared, I hope you think Pythagorean identities. So if we take that cosine squared u and we replace the cosine squared u with 1 minus sine squared u, we end up with this version right here, 1 minus 2 sine squared u. Pretty quickly, too. And then for the other one, if we start again, I like to start with cosine squared u minus sine squared u. You just have to be a little careful with this one. So if you start with that and you replace sine squared u with 1 minus cosine squared u, you have to be careful because this minus has to be distributed. So you end up with 2 cosine squared u minus 1. So never in my life have I memorized these formulas. If I need them, I derive them. Sometimes I write that down, sometimes I do it in my head, but I can figure them out without doing any work. Now you can go ahead and take a look at the worksheet if you did print it. And I didn't give you the formula for tan 2u because I would like you to try to derive it right now. So go ahead and try that. Did you get 2 tan u over 1 minus tan squared u? Here's how that happened. So 2u, again, can be written as u plus u. And then if we expand using our tangent angle sum formula, we get tan u plus tan u. That makes 2 tan u. And 1 minus tan u times tan u makes tan squared u down in the denominator. So that's your tangent double angle formula. Now, when it comes to these formulas, we use them to solve equation and verify identities. Those are kind of the only 2 things we do with them. So let's jump into our first example, which is going to be to solve this equation and find the solutions in 0 to 2 pi. When you look at this equation, that is a 2x, it's not a squared. You cannot combine these. You can't factor out a sign. So if you're thinking like, oh, I'll factor out a sign and this will become sine, it doesn't work like that. Because if you try to multiply that back in, what's sine times sine? It's sine squared. It's not sine 2x. So you cannot factor that and you cannot combine those. So just like we trained ourselves in the last section, you want to train yourself in this section. Anytime you see 2x, 2u, 2 theta, you want to think double angle formulas. So the formula for sine 2u, right on the top of this paper, says 2 sine u cosine u. So if I have sine 2x, I can replace that with 2 sine x cosine x. And at first you might say, wait a minute, that looks worse. Because now it's not all sine, now you have 2 different trig functions, sine and cosine. But that's okay, because this one factors. So if you look, you have 2 terms. This is 1 term. It has 3 factors, but it's 1 term. It's 2 times sine times cosine. This term is sine. They both have sine in common. So we can factor out a sine of x. Then we can set each factor equal to 0 and solve. So once again, I'm going to kind of zip through this solving part because you know how to do this. So we're going to kind of focus right now on working with the new formulas because I know that you know how to solve these two equations. So if you were to solve for where sine x equals 0, you get 0 and pi. And if you were to solve for where cosine x equals -1/2, you get 2 pi over 3 and 4 pi over 3. And again, if you do have questions on this part, the solving part, if you've forgotten something, just email me and ask. I can make you a little video, whatever you need to refresh your memory, because that usually happens when we're in class together, when we're doing chapter 5, is sometimes people just draw a blank. They're like, I don't remember how to do this anymore. So don't hesitate to ask questions. Here's the next one. We're going to solve another equation. So this time we have cosine 2x minus sine x. That's not squared, that's cosine of 2x. And we see a double angle, so we want to apply a double angle formula. Now, the thing is for cosine is there are 3 versions of that formula that we derived. So we have to pick what we think is going to be the appropriate version of this formula. Here they are with x's, because when I introduce them, we use u, but it works the same if they're x. So we have to pick top, middle, or bottom for which formula to use here. So if you go to try this one first, let's say. I think what you find is that you kind of get stuck. You can't combine those, you can't factor, so you're kind of stuck. So what happens with the cosine double angle formula is if you pick one that's not, I don't want to say the wrong one because it's not wrong, but if you pick one that doesn't help, then just try again, no big deal. So I think what a lot of you probably said was to use this one because then you'd have all sines and no cosines. So if that's the case, that would be a good pick. You can solve this one, by the way. You'd have to use Pythagorean identities to make that replacement right there. You'd end up in the same spot we're at now. But when we tried this again using 1 minus 2 sine squared x, if you notice, we don't have any cosines in the problem, and that's nice. We can't always avoid 2 different trig functions, but if we can make it all the same trig function, it's a good idea. So we want to solve this equation. So I'm going to rearrange the terms. So I put the sine squared term first, and then the sine term, and then the constant. And the structure of this is like negative 2x squared minus x plus 1 equals 0. So what we want to do is factor to solve. And there's one thing that's really bothering me here, and it's that the first term is negative. So just like with this one, we can actually change the signs and make it a nicer problem for us. So to change the signs here, we could, because this is an equation, we can multiply both sides by -1. And then our first term is positive and it's much easier to factor. Or another way to achieve the same result, you could divide both sides by -1. Because if you divide by -1 by every term, and divide by -1 over here, you get this equation. Or if you prefer to think of it this way, if you don't like that that leading coefficient is negative, move all the terms to the other side. So add 2x squared to the other side, add x to the other side, subtract 1, and you're in the same spot anyway. So what I would do is I would personally make this first term a positive because it's going to be easier for me to factor. Some people don't mind factoring with the negative. I don't like it myself. And once you've factored, you're going to have the same structure as 2x minus 1 and x plus 1. Check your outers and inners to make sure you have all the right SIGNs. And then you can solve these 2 equations. So we're going to set this equal to 0 and set this equal to 0. And once again, I'm going to zip through the solving part here because I know you know how to do it. And you get plenty of practice with it. This way we can spend more time looking at these new formulas and how we might apply them. So if you were to solve those 2 little equations, you would get these answers right here. 3 answers in this case. Okay, let's go on to a verify algebraically problem. I have 2 of them for you. They're going to be pretty quick. Okay, here's number 3. Verify algebraically, show all your steps. On the left-hand side, I have cosine to the 4th minus sine to the 4th of x. And my claim is that equals cosine 2x. You can start on either side. if you were to start on this side, you might not be sure if you should use the cosine squared x minus sine squared x, the 2 cosine squared x minus 1, or the 1 minus 2 sine squared x version of the formula. You're not sure. So this is equivalent to any one of these. So if we can turn the left-hand side into any one of these, we'd be finished. So I'm going to jump over to the left-hand side and start there. And I'm going to do that by factoring. This is a difference of 2 squares. This is the same structure as x to the 4th minus y to the 4th. So if I wanted to factor that, I could do x squared minus y squared, x squared plus y squared. So similarly, we're going to have cosine squared. You know what? I'm going to need a little more space. So I'm going to have cosine squared x minus sine squared x. And then I'm going to have cosine squared x plus sine squared x. Cosine squared plus sine squared x is 1 by a Pythagorean identity. So we have cosine squared x minus sine squared x. I'm going to go ahead and show that it's times 1 just to really show all my steps here. And then you have cosine squared x minus sine squared x, which is a new formula for you, but remember that that's equivalent to cosine 2x. So you can actually do this entire problem on the left-hand side and match the right-hand side. Just to remind you, you can work both sides. You just can't cross the barrier. You can't add something to the other side. You can't divide both sides by something. But if you wanted to, you could change this to cosine squared minus sine squared x, and then they match at that step. All right, last one of our double angle formula problems. We're going to verify this algebraically, showing all of our steps. All right, so I know these formulas are new. All right, so I know these formulas are new. However, if you look, I'm actually not going to focus on the right-hand side right now because that makes a big fraction with tangents, and I don't quite see that happening over here. So you could turn this into 2 tan theta over 1 minus tan squared theta, but I feel like that's not going to work out for me. So I'm going to focus on the other side. 2 sine cosine might look familiar. I know it's brand new to you today, but do you see how you have 2 sine u cosine u and that equals sine 2u? So instead of u, we're using theta. So we can rewrite this as sine 2 theta. So these formulas work both ways. So if you have sine 2 theta, yes, you can turn that into 2 sine theta cosine theta by a double angle formula. But you can also use this going the other way. If you have 2 sine theta cosine theta, you can replace it with sine 2 theta. And that's going to be a good way to go here, because similarly, if we look on the bottom, see we have cosine squared minus sine squared. That's not 1. That's not the Pythagorean identity. That's this double angle formula. So I can replace that with cosine 2 theta. And now we have sine over cosine of the same angle. So using our quotient identity, we can replace this with tangent 2 theta. Because the quotient identity that we're using here says if you have sine of an angle over cosine of an angle, then that's equal to tangent of the very same angle. So what's happening here is just our angle is 2 theta. Instead of being x or theta or just u, it's 2 theta. So sine of 2 theta over cosine of 2 theta ends up being tangent of 2 theta. And we're finished. Another pretty quick one. All right, so that is the double angle formulas. And again, this is not on the assessment Monday, but I thought we could utilize the time today to take a look at this lesson, especially because it is so related. Because to get these formulas, you derive them using the formulas from 5-4 that we've been working with. Thanks for watching, guys. Have a good day and a good weekend.